Okay, so I hope the screen is visible also. So today is the last session for this uh, NPTEL Quantum Mechanics I tutorials. So today is today we'll recapitulate some concepts that we have discussed throughout this course. So the problems are kinds of mixture of all the concepts that we have learned so far. And okay, so today we'll mainly discuss 5 problems, and then we will look for some other problems. Like today, I would like to make the session a little bit interactive. So since it's a recapitulation, so I think it will be beneficial if like if you tell me, so given some question, if you can tell me how to proceed to actually solve the problem. So do you agree to do that? So for that you have to unmute yourself. So like instead of going through the solution, so today I would like you to actually say, so how should we proceed? So since this is just a recapitulation, and then so I'd like it to be a little bit interactive discussion session. So what do you think? If you do not want to do that, then I will proceed as usual, like so. Okay, so what to do? Should I go through the solution like the other weeks, or would you like to say how should we proceed to actually solve a problem? Okay, so let us let us take the usual route. So this is our first question. So a particle. So consider motion in one dimension. So the particle is subjected to this potential. So okay, kx square plus b x to the power 6 with b greater than 0. So this is necessary so that this potential actually allows bound state. So for that b greater than 0 is necessary. So given this potential, so the energy eigenfunctions will be parity eigenstates. So we have to discuss why this is the case. So why are the energy eigenfunctions also the parity eigenstates for this potential in the motion in one dimension? Okay, so so what to do? So energy eigenfunctions are parity eigenstates. That means so our energy eigenstates are also parity eigenstates. So that means energy and parity are simultaneously diagonalizable here. So energy and parity should commute. So we will see if energy and parity, these two operators commute with each other, then of course we can have simultaneous eigenstates for energy and parity, and then the energy eigenfunctions will have some definite parity, and then we will say that the energy eigenfunctions will also be parity eigenstates. Okay, so we have to only check if the Hamiltonian, the given Hamiltonian operator and the parity, these two operators commute or not. So let us begin. So parity operator is intrinsically defined by its action on the position coordinate. So its action is to take x to minus x. So that is how parity is defined. So, and if you remember from our discussion in some week back, so there was a problem of parity, like this is the definition of parity operator. So under parity, the operator x changes like this. So remember, x is an operator, and on some operator a transformation acts like this, right? So px p inverse, so this is curly p, so px p inverse, so that is how an operator is transformed in quantum mechanics. Okay, so we are familiar with this. So px p inverse is minus x operator. So this is the definition of, this is by definition of parity. And some weeks back we actually showed that the momentum also transforms like this. So under the action of parity, operator p goes to minus operator p. So p is also odd under parity. This we have actually shown some weeks back. So we can see that this will also hold. This was also shown in that week's assignment. So probably week 8, probably, I guess. I don't remember, but it's most likely week 8. So in that assignment we showed that this is the case also. So p square is parity even, as we can simply see from here. And clearly, since x is odd under parity, you expect that x to the power 2n will be even under parity. So that so this is our intuitive expectation, but we can also show that this will hold. So for that, consider these sequences of steps. So there is x to the power 2n. I have just inserted an identity between x and x to the power 2n minus 1. We can always do so. And this identity operator, we shall write it at p as p inverse and p. So of course p is now p inverse and p multiplied together gives you identity. And then we will be grouping them separately. So consider this as one group and this as another group. Use the parity relation. So x goes to minus x under the action of parity. And for the second group, again decompose x to the power 2n minus 1 into x and x to the power 2n minus 2. Repeat the same steps, like inserting p inverse p in place of the identity. So you get this and this. Thus these steps gives you So from this step you actually reach here. So starting from p x to the power 2n p inverse, actually we reach x square multiplied by p x to the power 2n minus 2 p inverse, and we can go on to do this until uh, we have exhausted all the x to the power 2n powers, and that will give you x to the power 2n. So we have just proved our intuitive expectation that x to the power 2n should be parity even. So this is just intuitive expectation that we have just proved. Thus our total operator, so total potential energy, so look at here, so potential energy is kx square plus b x to the power 6, right? And we see, so potential energy, that means the potential energy is an even function of x, and we have seen that the even function of x is parity even. Okay, so that means under the action of parity Vx will remain unchanged. So that is purely because V is an even function of x. So under parity Vx remains unchanged, or in other words Vx is parity even operator. And we already know that p square is also parity even. That means the total Hamiltonian, which is p square by 2m plus bx, this total thing will remain parity even. So the different components are separately unchanged under parity. That means their total combination will also remain unchanged under parity. So we have got this relation, and this simply implies that parity and Hamiltonian are commutating. So since they commute, and we know Hamiltonian is Hermitian and parity is also Hermitian, since these two Hermitian operators are mutually commutating, that means parity and energy have simultaneous eigenstates. So that is why the energy wave functions will have some definite parity. So they will be either parity even or either parity odd. So we know that from our discussion of simple harmonic oscillator there also. So psi n, so the wave functions are characterized by the quantum number n. We know that for n odd the wave function is an odd function of x, and for n even the wave functions are even function of x. So, and why is that so? Because we know that the simple harmonic oscillator wave functions are actually multiplication of the e to the power minus x square and the Hermite polynomials, and Hermite polynomials have definite parity. So odd order Hermite polynomials are actually odd function of x, and even order Hermite polynomials are even functions of x. So that makes your simple harmonic oscillator wave functions have definite parity. And similarly, also here, since the total potential energy was even function, here also you will have your energy wave functions having definite parity. So this concludes our discussion of the first problem. So if you have any question, please ask. Otherwise, let us proceed to the second one. Okay, so don't think there is any question. So let us consider this. So now our problem is, so consider a system of n non-interacting electrons, okay, and they are confined in 1D infinite potential well of length L. So that potential where the inside the well potential is 0, outside infinity. So that infinite potential well. So n non-interacting electrons are confined in this 1D infinite potential well of length L. Okay. So we have to find the ground state energy of this system and degeneracy. So yeah, so this should be a very easy problem. So I would like you to say how, I mean, what should be the answer or how should we proceed. So yeah. Okay, so any guess how to do it? Okay, so let me go through the solution. Okay, so we should begin by remembering that, so since these are electrons, so electrons are fermions, so and all electrons are identical to each other. There is nothing to distinguish between them. So they are identical fermions. And we know that electrons obey the Pauli exclusion principle, right? So the whole branch of chemistry depends on this single important fact, that electrons obey Pauli's exclusion principle. So here we will have to use this fact also. So Pauli's exclusion principle, and another fact is that electrons have two spin states, right? They are spin half fermions. So they can either take spin up state or spin down state. So, okay, so electrons obey the Pauli exclusion principle. Thus, so, and you know, the energy levels are already known to us, the energy levels of the infinite square well potential. That is the same thing that we have been discussing for quite some time. So, and we know, so that means, so these electrons obey Pauli exclusion principle and they are spin half particles, right? That means they have two spin states. So that means at most two electrons can occupy one energy level of the given potential. Okay, so suppose the electron is at one electron is at the ground state of the square potential. So the k equal to 1 state, where the energy is pi square by h car square by 2m L square. Suppose okay, so in that state two electrons can fit, because okay, so one of them can take spin half, another of them can spin minus half, so the SZ component. So that is why two electrons can fit in a given energy level. So in this problem, they are only distinguished by their spin and energy quantum number. So they are non-interacting, but to characterize electrons, so the spin of the electrons are always there. So the spin will always be a quantum number for the electron, and here another quantum number is the energy level K, that comes from the specific potential that we are given. So we shall need two quantum numbers to completely specify the states of each electrons. So one will be K, the energy level, uh, the energy quantum number, and another will be Sz. So K and Sz, these two will completely characterize the states of each electron. Okay. So for a particular K, Sz can be plus half or minus half. So that is why two electrons can occupy one same energy level, but not more than two, because they are spin half particles. Okay. Now, how will they configure so that the energy of the total system is minimum? So you remember how the atoms are, so how the electrons in an atom are configured. So let us look at the electron configuration of oxygen. So they have total 8 electrons, right? And so what is the configuration? That is 1s2, 2s2 and 2p4, right? So total 8. So state, so 1 is 2, so S has n equal to 0, L equal to 0, M equal to 0, but two electrons are occupying this n equal to 0, L equal to 0 state. So why two electrons? Precisely because they have two spin states. So spin up state and spin down state. So similarly here also the electrons will configure themselves. So we do not know about the status of n. So whether n is even or n is odd, we do not know that. So let us examine each case. So let us first examine the case when n is even. Okay. So if n is even, and I have said that since n is even and at most two electrons can occupy one energy level, that means in the ground state the n electrons will occupy the first n by 2 energy levels with 2 electrons in each level, right? As you can understand, that will definitely minimize the energy. So that is the only possible configuration that will minimize the energy. So 2 electrons in each level, so maximally occupied states, and first n by 2 levels are occupied. Of course, we know that in the infinite squirrel potential, the energy varies with k square. K is the level quantum number, right? So the smaller the k is, the smaller the energy levels are, right? So that means if the electrons occupy the first n by 2 levels with 2 in each level, then definitely the energy of the whole n electron system will be minimum. And of course, the 2 electrons that occupy one state, that occupy one same level, have opposite spins. So two electrons occupying the same energy level must have opposite spins by Pauli's exclusion principle. So the ground state configuration will be two electrons in each of the first n by 2 levels, and that is how n electrons are fitted, right? And similarly also, and just simply the ground state energy clearly will be then this, right? So adding the energies of all the states up to level n by 2, right? And multiplied by 2 because there are 2 electrons in each of them. Okay, so these sums can be easily performed, or you can just use the formula, and then this is simplified into this final answer. So the ground state energy when n is even is this, and this ground state is non-degenerate. So the degeneracy, how the degeneracy comes, will be clearer when we discuss the odd case. So let us just go to that case. So before that, so please ask whether it is fine or if you have any question. So if not, then let us proceed to the odd case. Okay, now when n is odd, clearly, so n by 2 cannot be an integer, but the quantum numbers of these infinite squirrel potentials are all integers. So for n odd, the electrons then will fill the first n minus 1 by 2 levels plus 1 levels extra. So okay, so first n minus 1 by 2 levels will each have 2 electrons with opposite spins, right? But we have still 1 extra electron, and that must fill the next higher energy level, that is the level n plus 1 by 2 in the ground state. So this is the ground state configuration when we have odd number of electrons. So first n minus 1 by 2 levels are completely filled with 2 electrons in each, and in the n minus 1 by 2 level, in this level there is only 1 electron. So this is the ground state configuration for odd n. And now this last electron can have, so electron can have 2 spin states, and that is how this last electron can have either spin up or spin down. But our total energy, since these electrons are non-interacting and all that, so that is why our total energy does not depend on the spin of the electron, right? So that means whether the electron have spin up or spin down does not change the final answer of the energy. So that is how this ground state for the odd n case will be twofold degenerate, and the degeneracy is coming from this spin up or spin down state of this last 1 electron. Okay, so that is why this odd n case has a twofold degeneracy for the ground state. There was nothing like this in the n even case. So all of these first n by 2 levels were completely filled up. So that case, for even in case the ground state was non-degenerate. But in the odd n case, the ground state is twofold degenerate. Okay, so now the ground state energy can be simply found out. So remember, so up to n minus 1 by 2 level, there are 2 electrons in each, and in the level n plus 1 by 2, there is only 1 electron. So just sum these two pieces up and you will get the final answer as this. So this is the final answer for odd n case. So please notice this is 24. This 4 is not quite clear. It is looking like a plus sign, but it is actually 24. Okay, so this is the answer for this odd n case. So if you have any question, please ask. Okay, so if not, then let us proceed to the next problem. So this problem is straightforward. So given a spin 1 particle, so a spin 1 particle is in the given state. So a spin 1 particle is in the given state, okay? And the state is written in Sz basis. So you have to find the expectation value of Sx in this given state. So remember that this state psi is represented in the Sz eigenbasis. So clearly we know that for the spin 1 particle, the Sz eigenstates are 1 0 0, 0 1 0 and 0 0 1, right? And they have eigenvalues plus 1, 0 and minus 1 respectively, right? So remembering that fact, this state psi can be represented like this in a basis independent manner, right? So this is the representation of psi in a basis independent manner, like 1 comma 1. So 1 comma 1 ket is actually the column vector 1 0 0 in the Sz eigenbasis, and things like that. 1 0 is the column vector, so this 1 comma 0 ket is the column vector 0 1 0 in Sz eigenbasis, and this 1 comma minus 1 ket is the 0 0 1 column vector in the Sz eigenbasis. So clearly the linear combination is this, that is the one given in question. So the ket psi is expressed as this linear combination, and due to this 1 by root 14 factor, this is already normalized. So psi is a normalized linear combination of the three SZ eigenkets. Fine. So given this psi, how can we find the expectation value of Sx in this state? Okay, so clearly the numerator should be this one, and we do not bother about the denominator because that is 1, because psi is normalized already. So we have to find this. Okay, so this is not. So we have to actually find this matrix element. So our goal is to find this. So how to find this? So clearly, so Sx can be decomposed into S plus and S minus like this. We always do that whenever we have Sx and Sy, because S plus and S minus have simple actions on the Sz eigenkets. We have discussed about this for the last 3 or 4 sessions. So, and now let us act. So Sx is half multiplied by S plus S minus. So let us first act with S plus on psi. So this should be the result. So how do we find that? So these root 2 h cuts are those non-trivial coefficients, right? That root L into L plus 1 minus M into M plus 1. This is the factor that comes when you act with the uppering ladder operator. And uppering ladder operator also increase the M eigenvalue by 1 unit, right? So that is what we have here. So S plus acting on psi. So S plus acting on psi. So S plus is a linear operator, so it will act on these 3 basis states separately, 3 components of these states separately. So let us first look at this one. So S plus acting on 1 comma 1. So this will give you 0 because 1 comma 1 is the highest weight state. So for spin 1 particle, M has maximum value 1. You cannot have M equal to 2. That is why M. So once you have 1 comma 1, you cannot up the M eigenvalue by 1 unit. So that is why S plus acting on 1 comma 1 is 0. So no contribution from this one. You will get a contribution from this one. So S plus acting on 1 comma 0 gives you root 2 h cut 1 comma 1. So 0 is increased to 1 and root 2 h cut is coming from that front factor. So root L into L plus 1 minus M into M plus 1 h cut. So it is that front factor. And similarly, S plus acting on 1 comma minus 1 gives you root 2 h cut 1 comma 0. So simple stuff. So finally we have got S plus acting on psi is this. Right? So let us directly take this matrix element. So just take this inner product with bra psi. So I will not discuss how to take this inner product. That should be very elementary by now. So taking the inner product with bra psi, you get this answer as this. and this is the expectation value of S plus. Similarly, we have to do this for S minus and then add these two up and multiply by half. So similarly, let us look at the action of S minus on the state psi. So what does S minus do? S minus lowers the m eigenvalue by 1 unit, right? And similarly, there is a front factor, root L into L plus 1 minus m into m minus 1. Earlier it was m into m plus 1, but in this case it is m into m minus 1. Okay. So S minus acting on psi. So this is linear operator. So let us look at the action on these three components separately. So S minus acting on 1 comma 1 gives you root 2 h cut 1 comma 0. So now S minus acting on 1 comma 0 gives you root 2 h cut 1 comma minus 1, and S minus acting on 1 comma minus 1 gives you 0, because the minimum value of m for a spin 1 particle is minus 1, and you cannot lower this m equal to minus 1 further to m equal to minus 2. That is why S minus acting on 1 comma minus 1 is 0. Thus, this is the answer. So S minus acting on psi gives you this result. Now we will do the inner product with bra psi, and so this, and its answer is this one. Okay. Now we have to find this one. So Sx, expectation value of Sx, but Sx is half of S plus plus S minus. So just add these and these and divide by 2 the result of the addition. So this one. So this is the final answer. And of course the answer should have been a real number, because Sx is a Hermitian operator, and you know that the expectation value of any Hermitian operator is real. So we have a real number also that is consistent. But we saw that the expectation value of S plus is a complex number and S minus is also a complex number. This was expected because S plus and S minus are not Hermitian, but they are Hermitian conjugates of each other. So observe, these two results are complex conjugate of one another, right? And that is expected because S plus and S minus are Hermitian conjugates of each other. So fine. So if you have any question, please ask. Okay, so if not, let us proceed to the next one. Okay, so no, let us go with this one. Now about wave function. So a wave function of a system is given in cylindrical coordinates. Okay. So in the cylindrical coordinate, the wave function is given as this. Now A is a real positive constant. Okay. So this is the wave function of a system given in the cylindrical coordinates. Now we have to find the most probable value of rho. Now most probable value of rho. So this is a little different than what you have encountered so far. So most probable value. So how to find most probable value of a variable from some given wave function. Okay, so it will help if we can discuss in the form of some random variable. So you know all this probability density, the probability adding up to 1, all these stuffs are actually inherited from the theory of probability distributions. So you are definitely familiar with probabilities, like discrete probabilities, like throwing a dice and what is the probability of getting the result 5. So the probability is 1 by 6 if the dice is unbiased, etc. So these are discrete probabilities, but there is a continuous version of probabilities, and in that case there is something called random variables. And so you know the interpretation of the wave function. So psi x is wave function, right? And we say that mod psi x square is the probability density. So what does exactly that mean? So mod psi x square is the probability density. So this means that the probability of finding a particle between x and x plus dx is mod psi x square multiplied by dx. So this is the probability. So remove this dx, and that is why that is called the probability density. So if you add this probability, so add means here it will be integration because x is a continuous variable. So that is why this mod psi x square dx integrated over all the allowed values of x gives you 1. So this is total probability being equal to 1. So mod psi x square is the probability density or probability distribution function. So in the language of random variables and all that, so this mod psi square is called a joint probability distribution for 3 random variables rho, phi and z. So in this problem, the wave function that is given psi, rho, phi, z. So in this case, mod psi square will be a joint probability distribution for rho, phi and z. So from this joint probability distribution, we have to find the probability distribution of only rho. Okay. From this joint distribution, we have to find the probability distribution function of only rho, and then we will try to maximize that probability distribution function of only rho, and from there we will get the most probable value of rho. So this is the strategy to solve this problem. So is it clear, or do you have any doubt? So the thing is that, so mod chi square is a joint probability distribution, and from there, from that joint probability distribution, you have to find the distribution function of only the random variable rho. So this, we have to find the probability density function or distribution function for the random variable of rho only from the joint probability distribution of 3 random variables. Okay, so let the probability distribution function for rho is f rho such that this happens. So this is the definition of probability distribution function. And okay, f rho must be positive in all places. That is another requirement. So, and why 0 to rho? 0 to infinity, because rho is from 0 to infinity. This is the radial direction. So you expect it to be going from 0 to infinity. So not minus infinity to plus infinity, but only from 0 to infinity. Okay. Now how to find that? And now we know from our wave function the normalization condition of wave function. So this is the normalization condition of our original wave function that is given. So how to do the integration in cylindrical polar coordinate? So we know, so d rho, dz and rho d phi. So there is an extra rho coming from the integral measure, right? So in the cylindrical coordinate there is this rho d phi, and then mod chi square. So integrating of this cylindrical position space wave function over all the allowed values of coordinates, you expect the answer to be 1. So this is the normalization condition of the wave functions, right? So let us rearrange this integration. Okay. So this includes the contribution, the integration over dz and d phi. Clearly this is an integral, of course. This should give you a constant. This highlighted part gives you a constant. And there is this separated part. So the thing is that, so how to find the probability for one random variable from a joint probability distribution function. So for that we perform the integral over the other random variable completely, so that the final answer just depends only on rho. So only on that random variable for which we are asked to find the same. So in this case, we have to find the probability distribution of rho. That means we shall already perform the integration over z and phi, but we shall not perform the integration over rho. So this is a constant. This is not necessary for our purpose here, but we can definitely do this integral completely. So I have just retain that this is a constant b and that this is greater than 0. So remember, so this is a constant b and this does not depend on rho. Okay. And z and phi have been integrated out, so they do not depend on z and phi either after the integration. So after the integration, this is only a constant. So now compare with this with this one. So what do we have? So does not this look like that we have f rho equal to this? So this one and this one. So compare and you will see that our f rho, the probability distribution function for rho, is actually this one. Okay, this is the probability distribution function of rho. Now we have to just maximize this probability distribution function. So the value of rho that maximize this f rho is actually the most probable value of rho. So this is the probability distribution, and if this is maximum for some value of rho, that means this probability distribution is maximum for that value of rho, and that is why that value of rho is called the most probable value. Now how to find the maxima of f rho? Simple. This is one variable, real variable calculus. So f dash rho should be 0. This gives you rho equal to 1 by 2, sorry, a by 2. And you can also check that this is actually a maxima by taking the double derivative, and that will be less than 0 if you put rho equal to half. So rho equal to a by 2 is actually a maxima. You can check that. And thus this rho star equal to a by 2 is the most probable value of rho. Okay. So that is how you solve this problem. So the algorithm is to find, or the main step is to find the probability distribution function of rho from the joint probability distribution function of rho, phi and z. So while finding this, so we already performed the integration over z and phi in the joint probability distribution function normalization condition, but we do not perform the integration over phi, so that we can express the integration like this, okay, so that we can express our normalization condition like this, and from there comparing we can find that f rho, which is the probability distribution function of rho, is actually equal to this, and then take the maxima of this function. Whatever the maxima is will be the most probable value of rho. So this. So probably this was a little defined concept that you were used to. Okay, so if you have any question, please ask. So this was a little different kind of problem. We do not usually encounter these types of problem. So, and of course you can also find the expectation value. So what we do generally is to find the expectation value of rho. But this is most probable, so this is different from the expectation value of rho. So expectation value and most probable value, so they are different. So remember from the theory of from the kinetic theory of gas, like so RMS speed, then most probable value of speed, then there was average speed. So there were three different answers for these three quantities. So RMS was what? Root 3 kBt by m, but the most probable value was 2 kBt by m. Also average speed was 8 kBt by pi m, right? So see how 8 kBt by pi m is different from 2 kBt by m. So average speed was different from different from most probable speed. So here it is also the same thing. So this is the most probable value of rho, which is different from which is different from the expectation value of rho. Okay, so if you have no question, so let us proceed to the next problem. Okay, so these problems is nothing but involves combinatorial counting. So consider a 6-dimensional linear vector space. So we should have written Hilbert space here. So consider a 6-dimensional Hilbert space with orthonormal basis states as this. So these AI kits are orthonormal basis states of this 6-dimensional Hilbert space. Okay, where AI denotes the collection of compatible quantum numbers. So we have written all the possible collections into one single quantity AI. So now we have to find the total number of allowed configurations the total number of allowed configurations of two identical bosons in this vector space. So there are 6 possible states and there are 2 bosons, 2 identical bosons. So the word identical is important. So 2 identical bosons and 6 states in the Hilbert space. So how can these 2 bosons occupy these 6 levels? Or in other words, how can we arrange these 2 bosons in the 6 available states? So in how many ways we can arrange these 2 bosons in the 6 available states? So this is the problem. So any guess? So this is a simple combinatorics problem. So we have two identical bosons and 6 states. So in how many ways we can fit these 2 bosons in the 6 states? Like, of course, you know that most of these 6 states will be empty. So, like, you can fit these 2 bosons in one state and other 5 remains empty. Or you can fit one bosons in level 1 and another boson in level 2 and all the others remain empty. So this kind of counting. So in how many ways this is possible? So the thing is bosons are identical. So like, well, so okay, bosons are identical, but the energy states are not identical. So energy state 1 is distinguishable from energy state 2. So this is given, but the bosons are identical. So as we know, so there can be any number of bosons in each of these 6 basic states. So they are not fermions, so there is no Pauli's exclusion principles for bosons. So any number of bosons can take same quantum numbers. So any number of bosons can appear in these 6 basis states. So in other words, so in one state 2 bosons can appear, remaining all the others remain empty. So late one appear in state 1, another appear in state 6. So and all other 4 states remain empty. So these kind of things. So there is no bound on the number of bosons that can appear in a given state. So let there are Ni bosons in the state Ni. So let us translate this problem into a combinatorial problem completely. So Ni is greater than equal to 0. Of course, bosons cannot be of negative number. So there are Ni bosons in the state Ai. So Ni is greater than equal to 0 and this condition. So N1 plus N2 plus N3 plus N4 plus N5 plus N6 is equal to 2. So Ni is greater than equal to 0 and the sum of N1 up to N6 is 2. So how many ways this is possible? So in other words, we are trying to fit 2 identical things, 2 identical balls into 6 non-identical boxes with infinite capacity. So this is of course equivalent. So this is equivalent to this combinatorial problem. So in how many ways you can fit 2 identical balls in 6 non-identical boxes with infinite capacity? Of course, so there is a combinatorial formula, and using that formula you have this. So this is 7C2 and this is 21. So the total number of allowed configuration is 21. Okay, so this was for boson. So can you tell me another scenario? So if they were fermions, so what would have happened? Like, then what would be the total number of allowed configurations if these two were identical fermions instead of the bosons? So you have to just remember that fermions, identical fermions, satisfy the Pauli's exclusion principle. So can you tell me what will happen then? So 6 states, 2 identical fermions, and fermions obey Pauli's exclusion principle. So that means no two fermions can be in the same state. So then there will be an upper bound in the capacity of the states. So each state cannot fit more than one fermions. So either the state is filled or the state is empty. Sorry, filled means either the state has one fermion or the state is empty. So 0 or 1. These are the two possible capacities of each state when we have two identical fermions. So the number should then be 6C2. We have to choose two possible states, two different possible states from the available 6 states, right? Two different possible states. So then the answer will be 6C2, and then that is equal to 15. So that will be for Fermi. And another scenario that is possible is if the two particles are distinguishable. So we have just discussed two identical bosons and two identical fermions. So what would happen if the two particles are distinguishable? Like one is boson, one is fermion, or one is electron, one is neutron, so two different fermions, or one is photon, one is an electron, so two different, so okay, so let one be electron, another be a neutron, so two different fermions, and two different fermions do not have to obey the Pauli's exclusion principle. So now that is the restriction of the capacity of the boxes are lifted. Moreover, the balls, these two balls are now distinguishable. So like putting electron in the energy level 1 and the neutron in the energy level 2 is a different configuration than putting the neutron in level 1 and putting the electron in level 2. So this is the difference between distinguishability and indistinguishability. So earlier, putting one electron in box 1 and another electron in box 2 was same as putting one electron in box 1 and putting another electron in box 2, because electrons are identical. That means they are non-distinguishable. You cannot distinguish between, well, this is red electron and this is blue electron. No, you cannot distinguish like that. But with an electron and a neutron, you can make that distinction. Okay, so that is why then putting electron in level 1 and neutron in level 2 is different from putting electron in level 2 and neutron in level 1. Well, so if those two particles were distinguishable, then the total number of allowed configuration would be 6 multiplied by 6, so that would be 36. So for two distinguishable particles, the total number of allowed configurations would be 36. So 6 multiplied by 6. So they can, so irrespective of what the other is doing, one particle can go to any state it likes. And due to this distinguishability, we have to discriminate between two certain permutations. So earlier there was no permutations, only combinations, but now with distinguishability, permutations are also coming into play, and that increases the number of allowed configurations. So for two distinguishable particles, the answer would be 36. So, okay, so if you have any question, please ask. So otherwise, I have nothing more to discuss. Okay, so okay, so let us look at. So I hope the screen is visible. So these are some assignments, problems. Okay, this is this week's assignment problems. So all of them are recapitulations. Some of them were discussed in previous sessions also. Like this one, this problem 4, the double Dirac delta potential. So this was discussed in our very first session. Problem 5 we have discussed. 6 was also in previous week's assignment. So okay, problem 7. So okay, so consider a system of 5 non-interacting particles with identical spin that are in same state half comma half. So please notice that this is different from what we have discussed in problem 3. So our problem 3 was n number of electrons, okay, and finding the ground state of that n electron system. But this is different. Here the spins are constrained to have the Sz value plus up. So in this problem 7, this problem the spins are only taking the value, so all the spins are only up spins, so there are no down spins. So somehow you have fixed the orientation of the spins, like applying the magnetic fields maybe. So you have already fixed the spin orientations, and after fixing the spin orientations, you now have to find the ground state energy, and this will be different from what we have discussed. So now of course you can expect that then at each energy level there will be only one electron, because all of them are taking spin up values. So by Pauli's exclusion principle, no two identical fermions can be in the same quantum state. So, and since they have all same spin state, they have to have different energy levels. So that means these 5 particles in the ground state, they will be from level 1, 2, 3, 4 and 5. So they will feel from level 1 up to level 5, one particle in each of them, and then you just find the answer. So I would just want to point out that this is different from what we have discussed in today's assignment. So 8 is straightforward. I think that is what we have also discussed some times back. So 9 is discussed, and 10 is also a common question. So okay, so with that, let us conclude our session. So I have nothing more to discuss. If you have anything to ask, please do so. Or then let us end this session. Okay, so probably you don't have any question, so let us end this session.